Hi, welcome to Sunil Maths tutorial. In this video, we discuss about Sylow second theorem, second Sylow theorem. Abstract algebra, observe that. Let us see the statement of second Sylow theorem. Let capital G be a finite group, capital G be a finite group, and P be any prime number. Then all Sylow P subgroups of capital G are conjugate. It means the Sylow subgroups of the group capital G are conjugate to each other. Let us prove this statement. Capital G be a finite group. Finite group means it consists only finite number of elements. And P be a prime number such that P power n divides mod G and P power n plus 1 does not divide mod G. We define a prime number with a property. You observe that. P be a prime number such that P power n divides mod Z and P power n plus 1 does not divide mod C. Now take any two Sylow subgroups, capital A, B are two Sylow subgroups of capital G. If capital A, B are two Sylow subgroups of capital G, then order of A is equals to order of B is equals to P power n. The order of both the subgroups equivalent to P power n. Order of A and order of B is equals to P power n. Our aim is to show that A, B are conjugate. We have to prove that A, B are conjugate. It is equivalent to prove that. What is mean by conjugate definition? Capital A is equals to XB X inverse for all X belongs to capital G. So we have to prove that A is equals to XB X inverse for all X belongs to capital G. If possible, assume that A not equals to XB X inverse. It means we assume the contradiction point. What we have to prove that? So we know that by the definition of double cosets, order of AXB, order of the double coset AXB is equals to order of A into order of B by order of A intersection XB X inverse. Observe equation number 1. The equation 1 can be derived from the definition of double cosets. By the definition of double coset, order of AXB is equals to order of A into order of B divided by order of A intersection XB X inverse. It is very clear. A intersection XB X inverse. A intersection XB X inverse is a subgroup of A as well as it is a subgroup of B. This set A intersection XB X inverse is a subgroup of A. Therefore, order of A intersection XB X inverse is equals to P power m, and that m must be less than n. Because what is order of A? Order of A is equals to P power n. And this one, A intersection XB X inverse is a subgroup of A. Therefore, the order of this subgroup must be in the form of P power m, and m is less than n. Now equation 1 can be implies as. What is equation 1? You observe that order of AXB is equals to order of A into order of B by order of A intersection XB X inverse. Now we substitute all the points. So equation 1 implies order of AXB is equals to P power n into P power n by P power m, because the order of A and order of B both are equivalent to P power n. That's why the numerator contains P power n into P power n. You observe that. Order of A and order of B both are equivalent to P power n. And the denominator P power m. So this is nothing but order of AXB is equals to P power 2n minus m. This is obtained by using the formula A power n divided by A power m is equals to A power n minus m. That's it. Now m is less than n. If m less than n, then m less than or equals to n minus 1. Please observe the procedure. M is less than n. What it means? M less than or equals to n minus 1. Now m and n minus 1 both are subtracted from 1, 2n. If we subtract both of them with 2n, this less than or equals to becomes greater than or equals to. Observe that inequality. 2n minus m is greater than or equals to 2n minus of n minus 1. Here in the inequality we have m less than or equals to n minus 1. we subtract both the terms. We subtract both the terms with 2n. So this less than or equals to becomes greater than or equals to 2n minus m greater than or equals to 2n minus of n minus 1. We get 2n minus m greater than or equals to 2n minus n plus 1. 2n minus m is greater than or equals to n plus 1, which implies you observe that 2n minus m is greater than or equals to n plus 1. I can explain it with an example. 4 is greater than 3. Automatically p power 3 divides p power, you observe that 4 is greater than 2. So p square divides p power 4. P square divides p power 4. So by applying that example, p power n plus 1 divides p power 2n minus m. P power n plus 1 divides p power 2n minus m. It means p power n plus 1 divides order of AXB. This is nothing but order of AXB. P power 2n minus m is nothing but order of AXB. You observe equation number 2. From equation number 2, we get order of AXB is equals to p power 2n minus m. So now p power n plus 1 divides order of AXB implies as p power n plus 1 divides order of G, because order of G is nothing but sum of the orders of the partitions of double cosets. Sum of the orders of the double cosets. So p power n plus 1 divides order of G. Very clearly, this is a contradiction, because there is a property p power n plus 1 does not divide order of G. But we get p power n plus 1 divides order of G. This is a contradiction. So our assumption A not equals to XB X inverse is wrong. Then what is right thing? A is equals to XB X inverse for all X belongs to G. It means A comma B are conjugate. It means any two Sylow subgroups of capital G are conjugate to each other. Observe that.